In this short video, we're going to learn another technique which may help us take an inexact differential and turn it into an exact differential using an integrating factor. So the idea is, even if I have a differential equation which is not an exact differential equation, we may be able to find a new function. We're going to call it mu. And we multiply through both sides, every term by mu. And the resulting new functions, meaning the product of mu with m and the product of mu with n, will result in an exact differential. Now remember the criteria that we would need to have. I would need to be able to take the partial derivative of m with the new m with respect to y. That should equal the partial derivative of the new n with respect to x. So this criterion would have to hold. Now, if I work this out, I need to use the product rule with these partial derivatives. In order to get this equation, I would need to find a function, mu, which solves this equation. Unfortunately, this is a partial differential equation. All of these derivatives are partial derivatives, and we're not ready to solve that. So what we're going to do is make a simplifying assumption. One possible simplifying assumption would be that our function mu is a function of x only, or it could be a constant. In which case, mu doesn't change with y. There's no y in its formula. So its partial derivative with respect to y would be 0, and which means that this term would drop out. And if I do some algebra with what's left over, also the mu sub x, the partial derivative of mu with respect to x, is just going to change into d mu dx, because now we're assuming that mu depends on x only. And we get this equation here. Now, we still have to be careful here. In order to solve this ordinary differential equation using the techniques that we know, we are going to have to assume that, okay, first I'll write it in this form, and that this term in parentheses, the partial of m with respect to y, minus the partial of n with respect to x, all over n. We need to have that quotient depend on x only, or it could be a constant. And the way we would solve this dE is using an integrating factor of this form. This is really just the same integrating factor that we used before, but now we actually have a formula for the coefficient on mu. Now, instead of assuming that mu only depends on x, we could also make the assumption that it only depends on y, which would mean that its partial derivative with respect to x would be 0. And so this term, the partial derivative of mu with respect to x times n, that's going to be 0. And the partial derivative of mu with respect to y can be replaced with d mu dy. So doing some algebra, we're going to keep this expression m sub y minus n sub x. If we want to keep it that way, we need to have this additional minus sign out in front. And so now our differential equation has a minus sign in front of the mu, and then if we have the additional condition that this quotient depends only on y, we can solve this dE using this integrating factor, which looks like the previous integrating factor with two differences. We're dividing by m, and we have a negative sign. So again, as a memory aid to remember this integrating factor, if we're going to divide by m, then we must have a derivative, an antiderivative with respect to y. We must integrate with respect to y. And we can see that the subscript on m is y. That is what you must be taking the integral of. And on the other hand, if I had n in the numerator, here I have n sub x, so this would be a dx. And then finally, the last thing to remember is that when you do have a dy, you need this minus sign on the integrating factor. All right, let's do an example. So if I look at this, here's my function m, my function n. If I take the partial of m with respect to y, I just get x. And if I take the partial of n with respect to x, I get 4x. So these two are not equal to each other. So this is not an exact dE. So let's try to find an integrating factor. And honestly, there's no way ahead of time to know what integrating factor is going to work. So we might go ahead and check this quotient, the partial of m with respect to y minus the partial of n with respect to x, divided by n. So again, n is in the numerator, n has the x subscript. So my check says that this should depend on x only. Should be no y in there. Unfortunately, though, when I put in the values, I get an expression which depends on both x and y. So I can't use this. So let's check the other formula, the other quotient. Still we have the same m, partial derivative of m with respect to y minus the partial of n with respect to x. Now we're going to divide that by m. And the outcome should depend on y only. And yes, I get, after simplifying, -3 over y, which depends on y only, and we can use that. So that's not our integrating factor yet. That's just what goes into the integral. So first I'm going to have to integrate. Remember, there's a minus sign when I have m in the denominator. So that will change the minus to a plus. Find the antiderivative, and I'll get natural log of y cubed. And as always with our integrating factor, we don't worry about the constant of integration. So my integrating factor would be e raised to the power of the formula from that integral, and that will give me y cubed. So now my new dE, I get that by multiplying every term by y cubed. And that gives me this new differential equation. Now we still have to solve this new differential equation. We just can check our arithmetic to see if we have an exact equation now. So my new m is the xy to the fourth. Its partial with respect to y is 4xy cubed. My new n are these three terms, and I'll take the partial derivative with respect to x, and I see that I also get 4xy cubed. So I have checked all of my work in terms of the integrating factor, and now we have an exact dE. So how do I solve that? Well, I say that the new m is the partial of f with respect to x, anti-differentiate with respect to x. That gives me a candidate for my function f. Since I anti-differentiated with respect to x, the next step will take the partial derivative with respect to y, and I'll set that equal to my new n, which must be my partial of f with respect to y. So when I set those equal to each other, the first term can subtract out. And I'm left with g prime of y equals 3y to the 5th minus 20y cubed. I can anti-differentiate that using the power rule to get my g of y. So now this equation, 1/2 x squared y to the 4th plus 1/2 y to the 6th minus 5y to the 4th equals c is going to be the solution to the dE. It's the solution to the new dE. It's the solution to the original dE as well. All right, we'll work out some more examples in our next video.